Here's a tricky question. Imagine that we're given two objects, one of which is a solid sphere, the other of which is a hoop. We're told that they have the same mass and the same radius, and that their centers of mass are moving at the same speed, something like this. The question is, which of these two objects has more kinetic energy? Think you know the answer? Well, let's see. So let's move the objects back. The first step is relating the motion of the center of mass to the rotation of the object. So let's just pick the hoop, and I'm going to paint the hoop red. So the idea is, when the hoop starts rolling, it's going to make a red mark on the ground that we can track. And I'm going to let it roll once so that it returns to its initial orientation after having moved. Let me show you. So it makes a red mark on the ground, and the hoop has gone around once in the clockwise direction. Okay? What do we know about the length of the mark that it left on the ground? Well, if the hoop went around once and didn't slip with respect to the floor, it must be the case that the length of that line on the floor is just the circumference of the hoop, right? So that means that the hoop was displaced a distance 2 pi r, the circumference of the hoop. The amount of time it took to do that was just the period of the hoop's rotation. So we can say that delta t is big T, the period of the hoop's rotation. We can assemble the velocity of the center of mass using v equals delta x cm over delta t, and I'm taking absolute values here because we're not really worried about the sign, we just want to get the magnitude straight. Well, if that's true, we have expressions for delta x cm and delta t, so we'll put those in to see that vcm, the speed of the center of mass, must be 2 pi r divided by the period of the hoop's rotation. This combination, 2 pi divided by the period, you should recognize, in magnitude, that's the angular frequency. If it had a sign, we would call it the angular velocity. So what that means is that there's a simple relationship between the speed of the center of mass, the angular frequency, and the radius of the hoop, namely that vcm equals omega times r. This expression relates the translational motion, vcm, to the rotational motion, omega, of a round object. Okay, we'll use that for both of these two objects. Let me erase all this work. Let's go through and count up the kinetic energies. So the total kinetic energy of any system is a combination of the kinetic energy associated with the motion of its center of mass plus its rotation. K sub cm is the usual expression 1/2 mv squared, where I've just made it clear that the v we're talking about is the velocity of the center of mass. Kinetic energy associated with rotation is 1/2 I omega squared, where I is the moment of inertia here. So we'll need to figure out the moments of inertia for these two objects. I don't want this tutorial to go on for 20 minutes, so let's assume that we looked them up in the book, and the moment of inertia for a hoop is its mass times its radius squared. The moment of inertia for a sphere is 2/5 times its mass times its radius squared. Okay. Let's start by analyzing the expression for the rotational kinetic energy. So K sub rotation equals 1/2 I omega squared. Well, we have this relationship now between the speed of the center of mass, omega, and r, so let's use that to substitute in for omega in the rotational kinetic energy expression, like so. And we can simplify this a little bit so that k rotational equals 1/2 I times the speed of the center of mass squared divided by the radius of the hoop or sphere squared. This will be very useful for this problem, so I'm going to substitute in this expression over there on the left. Okay, we did. Now let's go through and analyze each object separately. So for the solid sphere, here's its moment of inertia. That means that we can plug in this value for I in the expression for the rotational kinetic energy. So let's do that. K rotation becomes 1/2 times 2/5 mr squared times vcm squared divided by r squared. The r squareds will cancel, so we get that the rotational kinetic energy is 1/5 m vcm squared for the sphere. If we want to calculate the sphere's total kinetic energy, we need to add in the stuff associated with the motion of its center of mass, so the total kinetic energy of the sphere is kcm plus k rotational. That means that it's 1/2 vcm squared plus this expression we just found, 1/5 m vcm squared. We can find a common denominator and add those two together to find that the kinetic energy of the sphere, as it's rolling and moving, is 7/10 m vcm squared. Let's write that expression down on the left so that we remember it. That's the total kinetic energy of a rolling sphere. Now let's do the same exercise for the hoop. So for the hoop, the moment of inertia is different. It's I equals mr squared. So we substitute that into the expression for the rotational kinetic energy to find that the rotational kinetic energy of a hoop is 1/2 m vcm squared. The total kinetic energy associated with the hoop's motion is k hoop equals kcm plus k rotational. So that's 1/2 m vcm squared for the motion of the center of mass, plus this expression we just found, 1/2 m vcm squared, for the rotational kinetic energy. It turns out for a hoop that half of its kinetic energy, if it's rolling along the ground, comes from translation, the other half comes from rotation. So the total kinetic energy of a hoop ends up being just m vcm squared. Let's write that over on the left. So now we want to do a comparison. Well, you can see the two expressions are different. So if we take the ratio of the kinetic energy associated with a rolling sphere to the kinetic energy associated with a rolling hoop, we find that at 7/10 mvcm squared divided by mvcm squared, we said that everything had the same mass and that the centers of mass were moving with the same speed, so those factors cancel, and we find that the ratio is 0.7, namely that the kinetic energy of a rolling sphere is 70% that of a rolling hoop, as long as you take into account both the translational and rotational kinetic energy. So under the conditions we've described, a rolling hoop has more kinetic energy than a rolling sphere, assuming again that the masses are the same, the radii are the same, and their centers of mass are moving with the same speeds. Counterintuitive, but true.